Hey everybody, this is Dr. Retzek. This is our first video for Math 406. The idea here is that for each day on our daily topics and reading list, there will be a corresponding short intro video to that reading. Ideally, you'll watch the intro video, you'll do the reading, and then you'll come to class with any questions or comments about that day's topic. This is the first one, so this is the intro to section 6A. Let's get started. All right. Section 6A is all about what are called inner products. So this is an intro to the idea of inner product. Now, to get our hands on inner products, we got to remember a few things about vectors with real coordinates from calc class. So back in calc class, it's probably calc 3, you guys learned about vectors like this, like the vector u, and they usually put a little arrow over it. Let's say the vector u is the vector 2, 1. So that's a vector. It belongs to the vector space R2, though you might not have used that language back in calc class. In our linear algebra class, that's the notation. So that vector belongs to R2. Now, vectors in R2 have magnitude. And you've heard that before, like a vector is a magnitude and a direction. You know, like the wind's blowing at a certain miles per hour at a certain angle out of the southeast. It's a magnitude and a direction. Now, visually, if you're interested in the magnitude of that vector, you just imagine the two-dimensional plane, and you think of that vector as being 2 over 1 up, and magnitude just means distance to the origin. And so by Pythagorean theorem, the magnitude of that vector is the square root of 2 squared plus 1 squared, so root 5. All right, so you guys know about vectors and magnitudes from calc class. You also know something from calc class called the dot product. Now, the dot product, back in the day in calc class, so in Rn, the dot product of two vectors is written like this: x1 through xn dot y1 through yn. And you remember how you used to take dot products. You just multiply the coordinates from the respective vectors and then add up the results. And so the definition, so this is a definition here, for the dot product in Rn, it's just x1, y1 plus dot, 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 all the way through xn, yn. Okay, so we're down with dot product from way back in the day. All right, now here's the thing. The cool kids don't say dot product. We just don't. What the cool kids say is inner product. But just because the terminology has changed, it doesn't mean that the mechanics have changed, and they haven't as far as Rn is concerned. So for us, in Rn, the inner product, so this is the term we're defining now, the inner product is, rather than writing out the two vectors and putting a dot in between them, we use these angled brackets. So if you're interested in the inner product of x1 through xn with y1 through yn, it is simply what you used to refer to as the dot product. So x1, y1 plus dot, 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 x, n, y, n. So the only change is the terminology, the vocabulary itself. We don't say dot product, we say inner product. Okay, so we understand inner products on Rn because we already understand dot products on Rn. The goal for the rest of this first intro video is to think about how we should understand inner product in the setting Cn. Now, in order to get our hands on the inner product in Cn, I think it's important that we remember a couple of things about complex numbers in general. So let's have a little review here, just real quick, on complex numbers. Okay, complex numbers. So a number in the complex field looks like a plus b times I, where a and b are both real numbers, and I stands for the number whose square comes out to -1. There is no real number whose square comes out to -1, and so we give this new symbol I to introduce a number whose square comes out to -1. It is no more fake or real than any other number. Okay, so complex numbers look like a plus bi, and we actually can envision those in what's called the complex plane. So sometimes people think of that number a plus bi as being a over b up in what's called the complex plane. So if you were interested in the absolute value of a complex number, and you were thinking that it should be somehow consistent with your idea of the absolute value of a real number, then you think back. Hey, that's the dog. She hates the mailman. You're going to hear stuff like that all the time. Shush. All right. What did you think of as the absolute value of a real number? Well, if you're imagining a number line, I guess it's just the distance to the origin. So the absolute value of 3 is 3, and the absolute value of -5 is 5, because -5 is 5 units from 0. All right, if you want a notion of absolute value in the complex plane, we should do the same thing. We should do distance to the origin. And if you're going to go with that notion of absolute value, then the picture makes it clear. The absolute value of the complex number a plus bi must be root a squared plus b squared, because that's the distance from a plus bi to the origin in that picture. Okay, now, it's worth noting that if you take a plus bi and you multiply times its complex conjugate, a minus bi, and you just FOIL like you always do, it's a squared plus b squared. Remember, I squared is -1. And a squared plus b squared is nothing other than the absolute value of a plus bi squared. So in the complex plane, if you're interested in figuring out the square of the magnitude, the square of the absolute value of a complex number, you simply multiply that number times its own complex conjugate. Great. These facts for complex numbers are going to come into play as we start to think about what the inner product on Cn should be. Okay. Here's our definition. for vectors x and y belonging to Cn, the inner product of x and y is nothing other than x1, y1 conjugate, plus x2, y2 conjugate, plus dot, 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 xn, yn conjugate. Typo, fix that up. Subscript yn conjugate. Now, the reason the conjugates are in there is precisely so that this matches up with our notion of inner product in Rn in the case that we take the inner product of a vector with itself. So in particular, if you inner product a vector x with itself, well, according to the definition above, it's x1 bar plus x2 bar plus dot, 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 xn bar. But each of those coordinates, x1 through xn, is just some complex number. And we just decided when you multiply a complex number times its complex conjugate, you get nothing other than the square of the absolute value of that complex number. So this expression boils down to absolute x1 squared plus absolute x2 squared plus dot, 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 absolute xn squared, which is exactly how we think of the magnitude of a vector in Cn. All right, so now we know how to do inner products in Rn, and we know how to do inner products in Cn, but there's much more to this story. The inner product is actually an abstract notion that extends to all sorts of different vector space settings, and we're going to try to extract the key properties of these inner products we've developed today into that abstract definition and see inner products in far more exotic and useful settings tomorrow. Okay, go read in section 6A up to the indicated spot on the daily reading and topics list, and come to class with questions, and I'll see you then. All right, bye.